All right, here we are back on, I guess it's officially Wednesday, March 18th, or Wednesday, March 25th, if you have taken spring break already. Officially Wednesday, March 18th, if you're not taking spring break early. You're taking it at the regular time. Anyway, look, all this stuff is still on the board here, so we can just pick up from where we left off. What we had done on Monday, when we were finishing up on Monday, what we did was we had started looking at calculating probabilities. Now, we, at this point, want to take the 1s wave function so we have started looking at the 1s wave function. We said that it has a normalization constant that we're going to write as a, and then it drops off exponentially. So, we got to get a hydrogen atom here. Here's a hydrogen atom. So if we think of this in terms of probability spheres, what we've got are concentric spheres of probability. We can integrate over all of those spheres, and from that, we can set the integration equal to 1 and determine the normalization constant. Now, we said as a shortcut for the S states, since the S states don't include theta and phi dependence, that we could simplify this down by, first of all, doing all the angular integrations up front. Okay, so what we've got then is the 1s wave function. We said looks like this. We haven't derived that yet. We are going to throw that in the Schrodinger equation, hopefully later today. Take a look at it, definitely later today. Take a look at it and show that it really is a solution, and show what its values are for energy and scaling factor. So here's the 1s wave function. Now the function we want is this. So we want to work from this abbreviated form. So I want to get, well, let me just get the wave function squared. In fact, let's just, I think we have enough outlined here, we can just set this thing up. So I'm going to take that wave function, I'm going to square it, put it into my probability formula, and it is going to look like this. It is going to look like integrating across variable r from 0 to infinity, so we don't miss any of those shells of probability. And what we're going to have is 4 pi variable r squared a squared e to the minus 2r over a, because it's the wave function squared, and then variable dr. And this integration needs to give us 1. So this is going to become normalization. So this is one of those tricks we learned back in chapter 38, and now we're going to try it with hydrogen atoms, specifically for the 1s state inside hydrogen. Let's see what we could do here to make life simple. We can certainly bring out the factor of 4 pi and the a squared. That will work. What we may, or let's go ahead and do this. What if we define a variable substitution? Now, we probably don't need to do that. It's not that difficult of an integral. But we'll practice doing some variable substitutions. And for these integrations of wave functions, what we very, very often like to do is take everything that's in an exponential and write it as a new substitute variable. So I'll designate my new variable u as 2r over a. Now, one of the nice features of doing that, and we saw this back in thermal radiation too. We did kind of the same mathematical trick. One of the nice features here is that the u now is unitless. It doesn't have any units. So what it does is it takes all the kind of physics information and moves it outside the integral. Let's see what happens here. So if I make this variable substitution, then what that tells me is that r is going to be given by a over 2 times u, and finally that dr is going to be a over 2 times du. So I got all my substitutions set up very carefully, and now I'm ready to plug those in. So what's going to happen is I'm going to bring out a factor of 4 pi a squared that we already discussed. And in addition to that, I've got 2 factors of r and 1 factor of dr. Now combined, that's going to give me 3 factors of a over 2. So these a over 2's are coming from this substitution and this substitution. Now what's going to be left inside the integral is, we brought up the a squared, is going to be u squared. These r's are now u's. The dr is du. And the e to the minus 2r over a is now e to the minus u du. And as suggested, this now is just a number. It doesn't have any physical variables inside it. And everything that has physical variables, in this case it's going to be the little a, that got moved outside. And so a, we're going to find out later today how to determine all of the different physical constants that are included in our scaling factor. We'll see what that is. But right now, let's concentrate on this piece right here. Now, if you were in calculus class solving this, you would probably be thinking integration by parts, and you'd be right. Now, it turns out, if I do integration by parts on this, there's a general formula that comes out from doing integration by parts. If I specifically have a formula for my integral that consists of an exponential to the variable, and there's my differential of my variable, my infinitesimal, and then I have that variable to some power, that's equal to n factorial. So kind of think about how that would work, and if you want to try it out, you can kind of convince yourself. If I pick a value of n and I start doing integration by parts, what I find is the integration surface terms that come out always have an e to the minus u in them, and when they're evaluated at infinity, they go away. And so they always have an e to the minus u times u to some power. So at the 0 limit, this goes to 0, and at the infinity limit, this goes to 0. And so what happens is, depending on what the power is, you have to integrate by parts n times. And every time you do that, you pick up the next factor of n. You reduce the factor of n each time, and it turns into being n times n minus 1 times n minus 2, and eventually you get to 1. Anyway, you can imagine this becomes not just in solving wave functions, but in different areas in physics. That's a really handy formula. We work with power functions times, or polynomials times exponentials all the time. Now, a warning, it only works for 0 to infinity. If it doesn't go from 0 to infinity, those surface terms in the integration by parts, they don't go away. So sometimes you just have to do integration by parts. Anyway, so what we're going to do is we're going to take all of this and say, hey, you know what that is? That's 2 factorial. So if that's 2 factorial, well, that's going to be easy enough to handle here. What that gives me is 1 is equal to 4 pi a squared. Cubing, a over 2 is going to give me a cubed divided by 8. And then the 2 factorial gives me a factor of 2. Now, I can cancel out the 2 and the 4 and the 8. So the 2 and the 4 in the numerator cancel with the 8 down below. And let's find some prominent location and box this. And it looks like what a is going to be equal to, a will equal 1 over pi a to the third square root. Okay, so there's a 1/2 power. So there we go. We've gotten our first normalization calculation, maybe our last, normalization calculation for one of the wave functions in hydrogen. All right, so nice, I can put that out there now. I can take this value of A, I can plug that back into, say, this formula right here. I can change my limits of integration. So you can imagine the kind of problems that are going to show up in the homework, right? Problems are going to say something like this. Here is a hydrogen atom. Here is R is equal to A. If this is a 1s state, how much of the probability is within R equals A? And so we carry out that integration and find out how the probability is spread out in different parts of the wave function, in different areas of the atom. What does the probability distribution look like? So so watch for these in the homework. There are some medium to medium difficult level problems that are going to show up in those, and they're doable. They're things that you actually definitely want to calculate. Okay, I think maybe the next step in all of this is let's solve the Schrodinger equation. So we've got the normalization figured out. We're claiming that this is the wave function for the 1s state. Let's verify that. Let's check and see if this really does satisfy the Schrodinger equation. So let's make a lot of space. So let's get rid of all this probability integration. And yeah, let's even get rid of this. Let's clear the board. And let's go back and to the Schrodinger equation, which we wrote down on Monday at the very beginning of class. Now, I'm not going to write down the whole Schrodinger equation. The whole Schrodinger equation had R dependence, it had theta dependence, it had phi dependence in it, and it was really complicated, and we saw that, and we appreciate the difficulty of that. But since all I'm looking at are S states, I don't have to include, since they're S states, the wave functions will only be functions of R. And that says that anything that has theta and phi dependence will go away. So I'm not going to write in those terms. Now, let's step back through this. I always feel like it's a good idea. I think on the midterm, when I was grading the midterm, on the Schrodinger equation problem, on problem 4, I was looking to start out with this, because I always feel like conceptually it's a good idea to go back and see how the Schrodinger equation develops, rather than just put the Schrodinger equation kind of full-blown out on the page. So let me step through this. First of all, we're going to start off with a statement of energies for these electrons. And then what we will do is remind ourselves that the kinetic energies can be written in terms of momentum. Now, momentum turns out to be prominent. Variable, and that's because momentum is directly related to the interference phase properties of the particle. And so we work in terms of energy and momentum.
velocity doesn't play an important role in quantum mechanics. So we're going to get the kinetic energy written in terms of momentum so we can convert this to operators. And then the potential energy, we went over this on Monday, the potential energy is given by Ke squared over R. If you don't remember how that works, go back and take a look at what we said on Monday. So since that's the energy statement, now I want to switch this into wave function speak. So in terms of a wave function then, the energy gets multiplied by the wave function. Now, the Px, Py, and Pz become operators, differential operators, and what those are going to lead to are minus h bar squared over 2m. But what we found then is that instead of using Px, Py, and Pz, what we have to use are Pr squared. Well, yeah, I'll write it this way and then we'll come back and talk about it. In spherical coordinates, the components of momentum at different locations are going to be given by PR, P theta, and P phi. So it's a mutually orthogonal coordinate system. I can represent the momentum in this coordinate basis compared with just rectangular basis. So either one is going to be able to represent my momentum. Now what we can do is well, let's do it this way. So what we can do is we can ignore these two momentum contributions. Those are actually related to angular momentum. The theta and the phi components of momentum are related to angular momentum. And since we're only looking at S states right now, those are going to drop out. Now it turns out that just the radial portion of this can be written a couple different ways. There's kind of a shortcut way, but then there's a more complete way of writing this, and make sure I'm getting this exactly right as I step through it. So, and this should match up with what we wrote down on Monday too. So this is 1 over r squared, partial with respect to r squared, partial with respect to r, wave function. Okay, and this is kinetic energy. So this series of operations will keep track of the kinetic energy. And so with this, it reads from right to left. So it says take the wave function, take a derivative with respect to r, whatever you get from that, multiply it by r squared. Whatever you get from that, take a partial with respect to r, whatever you get from that, divide that by r squared, and then you're through. The stuff in the parentheses. Okay, now the rest of this is going to be minus Ke squared over r times the wave function. Okay, that's the plan. Now, anybody remember what the wave function looks like for the 1s state? This is our Schrodinger equation. And now what we're going to do is we're going to check our 1s solution that we've been working with. Is this really a solution? We'll see. So a e to the minus r over a. So I'm not using the probability. I'm back to the wave function itself. So, this is kind of the basis of reality in quantum mechanics, is to come up with a wave function, a mathematical representation of for better or worse, of the properties of the particle. And so what we want to do then is, if that's the wave function, well, I can just plug it in here and here. This is going to be the tricky part, so let's get started. First thing we want to do is take that wave function and let me take a derivative with respect to r. What's that going to give us? And you go, that's not so bad. What we're going to end up with is minus 1 over a times the entire wave function back here. And then if I take that and multiply it by r squared, I'll drop the 1s. We know which state we're looking at. That will save us a little notation there. So I'm going to multiply this by r squared. And that's going to multiply everything by r squared. I can still see the original wave function in there, but now it's got some factors out front. What was the next step? And the next step is I got to take another partial derivative with respect to little r. So let's do that operation also. So again, it's kind of doing this. So I've got to take a partial derivative of this now, or yeah. Now this time it's a little more complicated because I'm going to have a couple of factors. I've got to use a product rule. So what I got to do is I got to take this, multiply it by the derivative of this, and then take this and multiply it by the derivative of this. Now when I take the derivative of this, that's going to bring down another factor of minus 1 over a, and that's going to leave me with r squared over a squared. Now when I take a derivative of this, that's going to give me minus 2r over a. And then, since it's an exponential, I'm still going to have the original wave function left. Wow, look at that. The original wave function will not go away. In this case, that's not always the case. Sometimes it's more complicated. You don't get that as a benefit. But this time we do. So what we can say is that everything we did here gave us r squared. Oh, we've got one more step. Almost forgot. What's the last step? And we said the last step is dividing through by r squared. So now we're going to do 1 over r squared times everything we did before. All right, what happens if we divide through by r squared? Well, that r squared goes away. And so what we're going to end up with is 1 over a squared. And then over here, we're going to get minus 2 over a, 1 over r. And then this time, you know, I just keep writing the wave function out. I'll just write it as wave function. And there is another parenthesis here, you're right. So let me get that. All right, so all that kinetic energy calculation that we did, and then just to match this up, that's the potential energy. So all of that calculation we did for the kinetic energy, that was the tough part of the problem. And what it gave us is the original wave function times a couple of terms, an additional factor out front. And so let's see what that amounts to. So now what I have is I've got energy times the wave function. Now, I'm going to have a minus h bar squared over 2m times everything that happened here. So, and this is everything that happened there. So let me see, you guys pay close attention because I don't want to lose a term here. H bar squared over 2m a squared. So that's what that first term becomes. Now if I take minus h bar squared over 2m and multiply it by this second term, the 2's cancel out. And the minus signs cancel out. And what I'm going to end up with is plus h bar squared over ma. Okay, don't lose anything. That's it, right? It's going to look like, I hope so. So this is going to become 1 over r. And I'll put kind of this brackety stuff on here. There we go. All right. Now, that all gets multiplied. Remember, the original wave function was there. Ke squared over r. And let me write this in a suggestive way also. Because now we're getting to the point where we're checking this, right? Now, how do I check to find out if this was a solution? If this is a valid solution for the Schrodinger equation? Well, first thing we can do in this result that we've come up with, notice that since I was fortunate. The wave function can just be canceled out. Since I kept getting factors of the wave function in this particular example, that all goes away. Now let's get rid of all that operator stuff for kinetic energy. Kinetic energy operations, gone. And let's see what we have left. So what we have left is this. I'm going to write this out. We have E is equal to minus h bar squared over m a squared. All right? And then what we have is plus h bar squared over ma times 1 over r. And then finally, I have this last term, which is minus ke squared 1 over r. That's what it looks like once I've cleared out the common factors of wave function. Now, how do I know if I've got a solution to a differential equation? And what I have to do now is take a look at each term. Now, that's constant. See these two terms right there? Those are constant terms. See these two terms right here? These are 1 over r terms. In order for this to be a solution of the differential equation, all of the little r dependence has to go away. Now, the way I can make sure that all the little r dependence goes away is to make sure that every term that contains a certain number of powers of r cancels out another term with the very same power. So let's think of it this way. Let's say that you were in calculus and they said, I have an equation ax plus b is equal to cx plus d, and I want that to be true for any value of x. What are the values of a, b, c, and d? Not trivial values of 0, but what are the values of a, b, c, and d that would make that true for any value of x? And you go, hey, if a is equal to c and b is equal to d, if those conditions are met, then that equation works independent of whatever values of x we've got. Well, we're trying to accomplish the same thing with our differential equation solution. So what we're saying at this point is, you know, the constant terms have to equal each other, and the 1 over r terms also have to equal each other. You can think of this as equaling each other or canceling out. But in either case, what this is going to give us are a couple of conditions. So the conditions that are going to have to be met for this to work is that the energy is going to have to be equal to minus h bar squared over m a squared. Now, that condition can be met because we don't know what the energy is. And in fact, what happens is when we solve the differential equation, this is how we determine the energy for the quantum state. So we found the wave function that solves this 1s state. And along the way, what it tells us is, oh, and by the way, this is what the energy is for that state. So that's pretty cool. Now, a problem we're going to run into here is, let's see, we know what h bar is. That's a predetermined constant, physical constant. We all know about h bar. What's m? And if we go way back to originally setting up that Schrodinger equation, the m was the mass of the electron. So the m there is also known, but I don't know what a is yet. So the energy so far is undetermined, but wait, we've got one more condition that has to be met. What's the other condition that has to be met here? And the other condition is that these 1 over r terms have to cancel out. So what that says is I'm going to put this up by itself and box it. That one's looking pretty good. And now I'm going to come down and say, okay, the second condition is that h bar squared over m a has to equal ke squared. So that's telling me what the value of A is determined by. The value of A is given by Planck's constant squared divided by m divided by ke squared. And I'll box this one too. Okay, so solving the Schrodinger equation, I mean finding out whether or not this was a solution, it worked. That's a good sign. And in addition, we were able to determine what the scaling factor A is and what the energy is for this particular state. So let's see where that takes us here. Let me clear up some stuff here. Everybody's good on this stuff, right? So let me get this out of the way. So yes, this really does solve. It's a solution to the Schrodinger equation for an electron in the electromagnetic potential of a proton, of a nucleus. Let me clear some space here. And let's take a look at, these are worth writing again. A, it says, is equal to h bar squared over m ke squared. Now let's remind ourselves what some of these constants are. K is 8.99, 10 to the, not minus 9, plus 9, newtons meters squared per coulomb squared. That is the electric magnetic force constant. That's the force constant for the electric force and the magnetic force in nature, which are really one force. And so it says that this value of A depends on that. M is the mass of the electron. Now I'm putting these in standard units for right now. That will work. And then h bar, what is h bar? So the whole point of just writing all this down is to just point out that we know what all these, and then E, sorry. We know what all these constants are. Now we don't know why they have the values they have. That's a little mysterious. But what it's saying is that the scaling factor, now remember, if I bring back the wave function, what was it that the scaling factor A told us anyway? And we said, oh, the scaling factor tells us at what rate the probability drops off for the electron in a 1s state. Another way of stating that is the scaling factor tells us how big the atom is. Because when we calculate, ooh, that doesn't look very curvy, let me curve it better. So remember, the scaling factor is kind of a determination of how spread out the wave function is, and that's going to determine, how the probability is distributed. And what this is saying is that the scaling factor is going to depend on whatever Planck's constant means. That's just kind of a fundamental constant of quantum mechanics. It's going to depend on how large the electromagnetic force constant is. In fact, looking at that formula, what would happen if we somehow got behind the curtain with all of the fundamental constants in the universe and we turned up the knob for the electric force? What would happen to the size of all of our atoms? And if you turned up the electromagnetic force constant or turned up the charge, what that would do is it would pull all the electrons closer towards the nucleus. You go, really, that's kind of interesting. I turn up the electromagnetic force, and sure enough, everything gets drawn in. If I turn down the electromagnetic force, atoms are bigger. If I turn up the electromagnetic force, atoms are smaller. Well, that's kind of cool. And then the other item it depends on is mass. So it says that if we have a really large mass, then the atom actually is smaller. If the electron had 100 times the mass or 200 times the mass, atoms would be 100 or 200 times smaller in size. It's kind of interesting too. Is there a heavy version of the electron we could try that out with? And there is. So it turns out that there's a heavier version of the electron. It's called the muon. Now it's not stable, but researchers, and this is not something recent, this goes way back, researchers have been able to take muons, generate muons in different reactions, and introduce them into these quantum states inside molecules. And what they've done is they've initiated hydrogen fusion. So if you take an H2 molecule, right, a couple of protons, the bond length between those two protons comes from that formula. So that's saying how big the atoms are. If you substitute in these muons, which are like 200 times heavier than an electron, then the bond length shrinks by a factor of a couple hundred, and the protons undergo nuclear fusion. So it's a good thing the electrons have this low mass. If they had a much, much higher mass, atoms and molecules wouldn't be stable. Nuclei would be so close together, nuclear fusion reactions would be going off all the time. Okay, it'd be a very different universe. Anyway, we can plug in all these numbers, and what we get is A is equal to 52.9 picometers. Now this is referred to as the Bohr radius, and I'm going to say just by coincidence, it's the very same formula that Bohr came up with his model that was based on a series of incorrect assumptions. So those were some pretty good incorrect assumptions. But we use this for all scaling inside atoms and molecules. So when we're looking at wave functions, kind of everything gets scaled in terms of the Bohr radius. Now, the other item that we've got here, in addition to this Bohr radius, and by the way, this does correctly predict the size of the hydrogen atom. So hydrogen atoms are, 100. And again, there's no definite size for an atom, but if you look at bond lengths with hydrogen, something of the order of 100 picometers or something for a diameter for hydrogen is a pretty good measurement of where most of the electron probability is. So that's pretty amazing well, it matches up with observation. Now the other formula we got, we didn't just get this scaling factor. Scaling factor. We also got the energy. Now what I can do is I can take my scaling factor, plug it in to my energy formula, and I left off a factor of 2. I apologize. I'm putting it in right now. Fortunately, we caught that. So there is a factor of 2 in that energy formula. If you remember, there was an h bar squared over 2m. And you guys, I know you guys in the back raising your hands, that's what you were asking about. I should have been paying attention better. Anyway, so that's going to be our energy formula is going to be given then by minus h bar squared over 2m. And then I can take 2 factors of A, and what that's going to leave us with is mke squared over h bar squared, and that whole thing is squared. And so what is it we finally get for the energy formula? And what we're going to get is minus 1/2. The h bar squareds here cancel the h bar squareds here. There's cancellation with one of the m's. But it leaves us with mke squared over h squared. Now remember, this is the 1s state. And that's how we derive the energy. And again, Bohr got this right by using a series of incorrect assumptions. But we're going to forget about that. We're just going to say, hey, now we know how to determine scaling factors, and we know how to solve for energies of all of these different states. So now we have an understanding of where that comes from and how to make those predictions. If I plug all of these numbers into here, what am I going to get? And plugging all these numbers in is minus 13.6 EV. Now remember, it's the 1s state. It does not have a factor of n squared. We didn't solve for all of the s states. We only were looking at the 1s state. So for the 1s state, n is equal to 1. So we can write that in. So that never showed up in our calculations that we did with the Schrodinger equation here. All right. Questions? So it's kind of remarkable. We started with that idea of what the Schrodinger equation is based on, statement of energy, and then substituted in our operators, and now we're at the point where we can take wave functions, plug those into the Schrodinger equation, and see how they develop. All right, let me take a quick look at my notes, but I'm thinking that is probably a good place for us to take a quick break, or to actually, take a quick break for this session. I think we've kind of looked at what we wanted to look at in this first half for today. All right, so we'll stop there for the day. Or for the session, sorry.